Okay, let's dive right into this explainer and get you completely ready for your linear algebra exam by demystifying the inverse matrix. If you're an engineering student trying to wrap your head around matrix operations, you are in exactly the right place. We're going to break down the logic, the shortcuts, and the algorithms you actually need to know.
So, let's start with a really intuitive question. By now, you know we can add, subtract, and multiply matrices, but can we divide them? In normal, everyday math, division is just how we undo multiplication. So we got to figure out, is there a way to hit undo on matrix multiplication?
Well, think about basic arithmetic for a second. If you have 5 times x equals 1, you solve for x by, dividing by 5. Or, to be a bit more precise, by multiplying by its inverse, 1/5. Linear algebra actually works a lot like that. If matrix A times matrix X equals the identity matrix E, you solve for x by multiplying by the inverse matrix, which we write as a to the power of -1. Basically, the inverse matrix is the linear algebra version of division.
All right, here's our roadmap for today. First, we'll cover the rules. Second, we'll look at the 2x2 shortcut. Third, we're tackling the 3x3 algorithm. And finally, a quick recap and a real-world engineering application.
Section 1. The rules and matrix invertibility.
Now, you probably remember that standard matrix multiplication means multiplying the rows of the first matrix by the columns of the second, right? With that in mind, let's do a super quick refresh on the identity matrix, usually called E or sometimes I. It's a square matrix with ones running right down that main diagonal and zeros everywhere else. This guy acts exactly like the number 1 does in basic math. You multiply any matrix A by the identity matrix E, and boom, the result is just matrix A again. So here's the absolute golden rule. A matrix multiplied by its inverse will always yield that identity matrix. A times A inverse equals E. Or flipping it around, A inverse times A equals E. This is literally the defining property of an inverse. If a matrix doesn't do this, well then it's simply not the inverse.
But hold on a second. Not all matrices actually have an inverse. Before you start sweating through calculations on an exam, you've got to check the gatekeeper rules. First up, it has to be a square matrix, same number of rows and columns. Second, and this is absolutely crucial, the determinant of the matrix cannot be 0. If the determinant is 0, there is no inverse. It's a mathematical dead end. So always check that first.
Section 2. The 2x2 shortcut, a true fast-track formula.
Okay, if you're dealing with a 2x2 matrix, you are in luck. The inverse is just 1 over the determinant multiplied by a rearranged version of your matrix. You just swap the elements on the main diagonal, flip the signs of the other two, and multiply the whole thing by 1 over the determinant. Let's look at this concrete example. Top row is 2, 1. Bottom row is 3, 4. The determinant is 2 times 4 minus 1 times 3, which gives us 5. So we pull 1 over 5 to the front, we swap the 2 and the 4, and make the 1 and 3 negative. And honestly, just like that, you've got your inverse. Memorize this formula, guys. It is a real game changer that will save you so much time on the test.
Section 3. The 3x3 algorithm, also known as the Gauss-Jordan method.
So for bigger matrices, we have to use a slightly more rigorous approach. We start by setting up a large augmented matrix. Imagine a dividing line. We place our original 3x3 matrix A on the left side of that line, and the 3x3 identity matrix E on the right. In our example here, matrix A has 1, 2, 1 in the first row, and the right side is just your standard identity matrix, so 1, 0, 0 in that top row.
Now what's the game plan? Your objective during the exam is simply to use elementary row operations to turn that left side into the identity matrix. You want those nice ones on the diagonal and zeros everywhere else. The trick is, whatever you do to the left, you do to the right. So if you perform those exact same row operations all the way across, by the time the left side becomes E, the right side will have magically transformed into your target, the inverse matrix, A inverse.
Let's actually see this in action. First up, we use that top left one to clear out the numbers below it. By subtracting row 1 from row 2 and then, say, subtracting 2 times row 1 from row 3, we create nice zeros in that entire first column under the 1. Then we just repeat the process, right? We move diagonally to get a 1 in the center and clear out the rest of that column. Maybe we multiply row 2 by -1, then use it to zero out the values above and below it. Notice how applying these exact same operations changes the right side at the exact same time? Once you finally get that clean diagonal of 1s on the left, whatever fractions or wild numbers are sitting on the right side of the line, well, that's it. That's your finalized inverse matrix.
Section 4. Recap and engineering application. Let's talk about why this actually matters.
Okay,
Here's your foolproof, 4-step summary to mentally bookmark for the exam. Step 1. Always check that the determinant isn't 0. Step 2. Set up your augmented matrix. A on the left, identity on the right. Step 3. Apply your Gauss-Jordan row operations carefully. And Step 4. Extract your shiny new inverse matrix from the right side.
Now, you might be wondering why go through all this trouble. Well, to quote your course notes, calculating the inverse is worthwhile when repeatedly solving equation systems with the same matrix A and different right sides. Let me put that into perspective. In real-world engineering, matrix A usually represents the fixed, physical properties of a structure, like say the stiffness of a bridge. The right side, that vector B, represents external loads: cars, wind, a heavy snowfall, you name it. You obviously don't want to recalculate the bridge's structural properties every single time the wind changes direction, so you calculate the inverse just once. Then you can quickly solve for the internal forces over and over again simply by multiplying that inverse by the new load vector. It is incredibly efficient.
So the next time you're staring down a massive, intimidating system of linear equations, just remember that the inverse isn't just some abstract math puzzle, it's actually a vital, real-world tool for handling complexity. When you step out there and face a complex engineering system, how will you use the inverse to handle the load? Master these rules, trust the Gauss-Jordan process, and you are absolutely going to crush that exam. Thanks so much for hanging out with me for this explainer, and happy studying.